Welcome to MrCScience.com's video on reduction oxidation reactions, also known as redox reactions. Redox reactions kind of link between ionic and covalent bonding and kind of track the flow of electrons. And that flow of electrons can be used for such things as powering batteries. So let's talk about this a little bit. Redox reactions or reduction oxidation reactions track that flow. So redox reactions care where the electrons live. So if we want to track that, we track that via something called an oxidation number. So an oxidation number is kind of or finding out where the electrons live. So in, say, sodium chloride, we know this is ionic because it's got a metal and a nonmetal. And we know that sodium has a +1 charge and chlorine has a -1 charge. Well, it turns out that is also the oxidation number, where those electrons live. So the electron lives with chlorine, so it's got an oxidation number of -1, and sodium has an oxidation number of +1. Let's take a covalent compound like hydrochloric acid, HCl. Again, we got the chlorine. Well, what we're going to do is we're going to treat the HCl like it was ionic. So we know that chlorine is more electronegative than hydrogen, so even though they share electrons, the electrons spend a lot more time around chlorine than they do around hydrogen. So we're just saying, what if that went fully that way? So if that went fully that way, chlorine would have that -1 charge again because it's stolen the electron from hydrogen, and hydrogen would have the +1 because it likes to give its electron to anyone who'll take it. Now again, this isn't truly an ionic thing. They still share that electron, but its oxidation number can be treated as if it were ionic. So oxidation number of hydrogen here is +1, oxidation number of chlorine here is -1. So that just kind of tracks where those electrons live. Now the oxidation number, its actual definition is the charge of an atom in a molecule, the charge that an atom in a molecule would develop if the most electronegative atoms in the molecule took the shared electrons from the less electronegative molecules. So that charge, now what's interesting about these oxidation numbers is that the oxidation numbers need to add up to the net charge of the molecule. So we know the net charge of sodium chloride is 0, 1 minus 1 is 0. Net charge of hydrogen chloride or hydrochloric acid is 0 plus 1 minus 1 equals 0. Let's take an ion. Let's say hydroxy ion. We know a hydroxy ion is a -1 charge. So what's the oxidation number? Well, if we treat this like an ionic compound, oxygen is in the 6th row of the table, so it would take 2 electrons to be stable. So it would have a charge of -2. Hydrogen, on the other hand, has only 1 electron to give away, leaving a net charge of +1. Now, these are the oxidation numbers. But if we notice, -2 plus 1 gives us -1, which equals the net charge of the molecule. So oxidation numbers always have to add up to be the net charge of the molecule. Okay, so there's a bunch of rules for what an oxidation number should be, but really drops down to a few. First of all, if an atom is all by itself, say we have a iron atom, its oxidation number is always 0. Say we have our hydrogen, but it's in its homonuclear diatomic hydrogen gas. Again, its net charge is going to be 0 because it's all by itself. Same with, say, chlorine. Chlorine is a homonuclear diatomic as well. Its net charge is 0. So any time that it's all by itself, its net charge has to be 0. Or actually, that's a lie. Say we have iron with a +3 charge. Well, its oxidation number, its net charge, has to be 0 or equal to the charge of the atom itself. So if the atom has a charge, then its oxidation number becomes that charge. So that makes some sense. If we had oxygen somehow gained an electron but not both and had a -1 charge, oxygen's oxidation number would be -1. But generally otherwise, whenever it's all by itself, or just sharing electrons with itself, its oxidation number is going to be 0. Otherwise, we treat it as if we're an ionic compound using the columns and rows that it's in to figure out the number of electrons that it would give away or take. The other exception to this rule is hydrogen. Hydrogen, like we said, hydrogen normally gives away its electron, with the exception of if it's paired with a metal. If it's paired with a metal, say sodium hydride, in reality what's going to happen is sodium, the metal, will give away its electron and hydrogen will gain that electron. So if the hydrogen is paired with a metal, it will actually gain an electron instead of lose an electron. This is unusual. We haven't seen this at all in the course yet, but moving forward into a little more advanced chemistry, you can see hydrogen pairing with metals. But otherwise, hydrogen is almost always going to give away its electron, again, unless paired with a metal. So let's do a couple examples of this. Here, let's scroll down, scroll away. Okay, let's take carbon dioxide. That's very bad, 0. There we go. Carbon dioxide. Okay, so we're going to treat this like as if it were ionic, even though it is truly a covalent. Start with the easy one, oxygen. Oxygen is in column 6, which means it will gain 2 electrons, so it has a -2 oxidation number. Now, the difference here is that we got 2 of these, so 2 minus 2 gives us a +4. So in order for carbon to remain neutral as we wrote it, the carbon needs to be a +4 for its charge, its oxidation number. Let's take a little bit harder one. Let's take phosphate. Whoops. I learned to draw slower. There you go. Phosphate. Phosphate is a homonuclear, not a homonuclear diatomic. It's a polyatomic ion. It has a charge of -3 all by itself. So we know that oxygen has a -2 charge. It's in that 6th column. It will want to gain 2 electrons. There are 4 of these. So 4 times 2 is -8. But we have a -3 charge. So -8 minus -3 will give us or 8 minus 3 will need a +5 charge in order to counteract the -8 here and leave 3 left over. So now let's label what's going on here. In a reduction oxidation reaction or redox reaction, one molecule will be reduced, the other will be oxidized. Now, what does that mean? Well, if a number is reduced, it actually gains electrons. Seems contrary to what it means. It's reduced, but it gains electrons. If an atom is oxidized, it loses electrons. Now, there are different ways to remember this. How I remember this is generally when oxygen pairs with anything, it tends to be the most electronegative atom, so it will want to steal electrons from whatever it gets. So if something's oxidized, it will lose electrons, like our carbon dioxide. So two oxygens wanted to take away a total of -4 electrons. So carbon gave up those 4 electrons. So in this case, carbon is oxidized. Oxygen is reduced because it gains. So here again we got the same thing. Oxygen gained electrons, so it was reduced. And phosphorus lost electrons, so it was oxidized. Happens to be it was oxidized by oxygen. So those are fairly easy to remember. Let's take a slightly different one. Let's take ammonia. NH3. So if we look at this, hydrogen not paired with a metal, so according to our rules is going to have a +1 oxidation number. So there are 3 of these total. So that gives us a +3, so that means nitrogen has to have a -3 oxidation number. So now, which one was oxidized and which one was reduced? Well, if it was reduced, it means it gained electrons. So nitrogen normally is 0, so -3 must mean it has 3 electrons. So that means that nitrogen is reduced. And hydrogen lost electrons, and it was oxidized, even though oxygen wasn't the culprit this time, but it lost electrons. So that's the basics of it, but let's put it to use now. How can we tell when we have a redox reaction? So let's take a reaction here. Let's take magnesium. Oops. Let's draw slower. There, magnesium, which is a solid. And with that, we add it to hydrochloric acid, which is almost always aqueous. And that gives us hydrogen gas and magnesium chloride, a salt, which precipitate, or no, because it's ionic, it would dissolve, so it's aqueous. Okay, so let's start with oxidation numbers. Now we got, first of all, magnesium here. Let's get rid of the extra little purple and blue there. Okay. Magnesium is all by itself, so its oxidation number equals the charge of the atom, which is 0, so its oxidation number is 0. Okay, let's move to our hydrochloric acid. Well, we know chlorine's in the 7th row, so it wants to gain an electron, so it's got a -1 oxidation number. So in order to balance out, and we know hydrogen, when it's not with a metal, gives away its electrons, so +1. Notice that we don't take into account the stoichiometric coefficient at all in this, so we're going to ignore as if it didn't even exist. Okay, so then we get to hydrogen gas. Now here, hydrogen is all by itself. It's just bonded to itself, and we know from our rule that anything that's by itself has the charge of the atom, which is 0, so it's 0. Now here, magnesium chloride, a little different. We got 2 chlorines. Chlorine has a -1 oxidation number. Since there are 2 of them, we care about this 2. It's going to be -2 charge here, so that means magnesium has to have a +2 charge. So let's look and see what happens. So magnesium went from a 0 to a +2. What does that mean? It means it lost 2 electrons. Now hydrogen went from a 1 to a 0. In order to do that, it gained an electron. Okay, so we have loss of electrons, we have gains of electrons. This is a redox reaction. This is a redox. What was reduced? Reduced means it gained electrons, right? So what gained electrons here? Well, hydrogen gained an electron, so hydrogen was reduced. Oxidized means it lost electrons. Well, magnesium lost 2 electrons, so magnesium was reduced. Let's do another of these. Let's do a decomposition reaction. If we run electricity through water, it will decompose into hydrogen gas and oxygen gas. Now in order to balance this, we need 2 oxygens, 2 of those, and we need 2 of those. It is balanced. Okay, so we want to start out with our oxidation numbers. So we know, right here, let's start with hydrogen. We know hydrogen is always loses an electron if it's not with a metal. So hydrogen has a +1. Now we know oxygen is in column 6, so it wants to gain 2, -2, and we can compare. We got 2 +1s plus -2 gives us 0, which gives us the the charge of the molecule. So that looks good. Hydrogen here all by itself. We know whenever an atom is just by itself, it gets the charge of the molecule, or in this case, a 0. Same with oxygen, 0. So is this a redox reaction? Well, if we look right here, hydrogen went from +1 to 0. That means what? It means it had to gain an electron. Oxygen went from -2 to 0. So that means it had to lose 2 electrons. So this is a redox reaction. We have changes in oxidation numbers. What was reduced? Well, remember, reduced means gained electrons. So hydrogen gained electrons, so hydrogen was reduced. Oxygen. What happened to oxygen? Well, oxygen lost 2 electrons, so it was oxidized. Kind of funny, oxygen was oxidized by oxygen. But so this is a redox reaction. Okay, now let's do what you'll learn later in college chemistry is called a double replacement reaction. So let's start with the salt, sodium chloride. Up, sodium chloride. And we're going to add silver fluoride to it, AgF. That's going to give us silver chloride, AgCl, plus sodium fluoride, NaF. I believe everything's balanced. Right, okay. So let's look here. Sodium's in the first column, so we know it's going to give away its electron, +1. Chlorine's in the last column. It's going to gain an electron, or second to last actually. It's going to gain an electron, -1. 1 plus -1 is 0, which equals the charge of the atom. Silver we're unsure of, but we know fluorine is in the 7th column, so it's going to gain a -1. So in order to have a 0 charge, silver has to get a +1. So now we're going to whip around the other way. Well, silver again we're unsure, but we know chlorine's -1. So silver has to be +1 so that it's a 0 charge. And then sodium's in the first column, +1. Fluorine's in the 7th column, -1. And that's equal. So now if we look at this, did oxidation numbers changed? Sodium +1, +1, chlorine -1, -1, silver +1, +1, fluorine -1, -1. This is not a redox reaction. So there are reactions that aren't redox reactions. So this is one of them. So if this came up on the test, that would be your answer. Because one thing that's common with the redox reaction, redox reactions will always have one atom reduced, or at least one atom reduced and at least one atom oxidized. You will never have something that is just reduced or something that is just oxidized, because then those electrons would have to disappear and that wouldn't work very well. So let's take a look at batteries. Redox reactions are common in a lot of our batteries. So let's take this. We got copper, copper 2 ions in an aqueous solution, plus solid zinc gives us zinc ions in aqueous solution, plus solid copper. So is this a redox reaction? Well, we got all 4 atoms all by themselves, so normally we'd say, well, 0, 0, 0, but remember it's also equal to the charge of the atom, so copper all by itself has to equal the charge of the atom, so it's a +2 oxidation number. Zinc all by itself, 0. Zinc with +2 ion has to be equal to that, so +2, and copper, 0. So what happened? Well, copper went from +2 to 0. So it had to gain 2 electrons. Zinc went from 0 to +2. So in order to go to plus, it had to lose 2 electrons. So this is a redox reaction. What is reduced? Well, reduced is the one that gains electrons. Which one gained electrons? That would be our copper. Oxidized. What was oxidized? Had to lose electrons. That would be our zinc. Okay, so we got a redox reaction. Now this also works as a battery. So they'll have you draw some diagrams of batteries. Batteries are generally drawn with two containers. Those containers, as far as your book concerns, is usually water for an aqueous solution, although aqueous doesn't necessarily mean it has to be water. It could be alcohol, something like that. But generally aqueous. Okay. this is called a salt bridge, runs across the middle. We'll discuss why that's there in a second. And then you have a wire running between the two. So let's start what we have here. We have copper plus 2 aqueous, so that's in solution. It's aqueous, so we have copper plus 2 aqueous solution here. And we have a zinc solid, so we're going to use zinc as a solid right here. Zinc, you can almost read that, but you know what I'm saying. Okay, so zinc solid. So that gives us zinc plus 2 aqueous. So we got a zinc solution here and copper solid. Well, what's really happening here is we've created a battery with a salt bridge. Ah, that's really bad. Good thing you can listen to me because you wouldn't be able to read that. Okay, that's a salt bridge running between there. So what's going on here? Well, what happens is where our electrons go, they go from the copper plus 2 to the copper. So the electrons flow towards the copper. So we got an electron flow going across here to the copper. So now zinc loses 2 electrons. So zinc goes from that, it loses these 2 electrons. So, oh sorry, and copper gains the 2 electrons. Zinc loses, copper gains. So what about this salt bridge here? Well, that salt bridge there is actually just kind of form the positive ion or the continuation of the link. So we've got a circuit here going around. So where the electrons flow out of is the negative terminal. So we got the, geez, that was really bad. We got the negative terminal here. Where they flow into is the positive terminal. The negative terminal is called the anode. The positive terminal is called the cathode. You can remember how this works. Some people say, well, cats are a very positive creature. Cathode, cat, positive. That's kind of how I remember it. So if you know my record with cats, it seems contrary to that, but hey, what the heck. So, so this is how you're going to draw your battery. You're going to have your anode, your cathode, you're going to have your solutions, you're going to have your 2, what do you call these things again? Your 2 electrodes, and then those electrodes are going to be labeled your anode and your cathode. The negative is where the electrons flow out of. The positive is where they flow to. So let's go ahead and try a different battery. Okay, so let's do a different one, different battery. This is also called actually a galvanic cell. So let's start with 2 silver plus, come on, you can do it, there we go. That is aqueous. Usually if you've got a ion or a charge there, it's going to be aqueous because ions dissolve easily in water. Plus we're going to have some magnesium solid. Make that look more like a plus. That's going to give us 2 silver solid plus magnesium plus 2 ions, aqueous. Now we know this is a redox reaction because what's the oxidation number of silver? Well, it's the charge of the molecule, so we got a +1 here. Magnesium's all by itself. Again, charge of the molecule is 0, so this is 0. Silver, all by itself, no charge this time, is 0. And magnesium now has a +2 charge. Oops. That's right, the oxidation number with the charge in front, +2. So silver went from +1 to 0, so it gained an electron, so it means that it was reduced. Magnesium went from 0 to +2, it means it lost 2 electrons, means it was oxidized. Okay, so this is a redox reaction, and this can be used to drive a battery. So what we're going to do then is we're going to draw our cells. We're going to draw our solution, water. We're going to draw our salt bridge. they'll often do with a salt bridge, I mean, they can make these in reality, is they'll put a little bit of cotton balls on each side to kind of reduce the exchange across there so the ions travel, but the diffusion of the two is slowed. Then we got a wire going from each side. Each side will have an electrode. Okay. So let's start with this side. We've got silver solution, aqueous, Ag+. We got our magnesium solid, so that's going to be our electrode. Okay, on this side we've got our Ag solid, that's going to be our electrode on this side. And we got our Mg plus, or 2 plus as our solution there. Okay, so where are the electrons going to flow here? So we know that silver was reduced. It went from Ag plus 1 to Ag 0. So it means it gained electrons. So the silver solid gained the electrons. So that means our electron flow is going to be this direction. Since our electron flows this direction, it has to flow from the negative terminal. So this is a negative terminal, or our anode. Flows to our positive terminal, or our cathode. Okay, our electrodes are magnesium and silver. And that is our bridge. Our salt bridge, actually, the positive ions can form this way, the negative can go that way. So, or I'm sorry, I got that backwards. Positive, negative, because our negative is going to form a complete loop. Wow. So always going to be flowing the same direction. And because positive charges are aqueous, they can actually flow through the salt bridge. So where normally positive charge could not flow through a wire because positive charge is the nucleus of the atom, and nucleuses stay put. The electrons are what move around. So, okay, so these galvanic cells, while they can conduct electricity, isn't generally how we make a battery. Let's look at your car battery, which is called a lead acid battery. A lead acid battery runs off the following reaction: Pb, which is lead, lead oxide, which is a solid, plus lead, which is a solid, plus sulfuric acid, thus the lead acid, H2SO4, which is aqueous, gives us 2 lead sulfates, which is solid, and water, which is liquid. Now this one looks a little more complex. Let's take a look at our oxidation numbers here. So lead we're unsure of, but oxygen again is in that 6th column, so it wants to have a -2 oxidation number. It wants to gain 2 electrons. Since there are 2 of them, that means lead here has to have a +4 to give it its neutral charge. Lead all by itself, of course, since it's got no charge, means that it's 0 oxidation number. Hydrogen, we know, isn't with a metal, so it's going to give away its electrons, so +1. Oxygen, we know again, is -2. Now there are 8 oxygens here, so that's going to give us a -8 here. There are 2 hydrogens, that's going to give us a +2. That means in order to be 0, we have a -6 difference, so sulfur has to be -6. Okay, here lead again we're unsure of. Oxygen -2. Whoops, made a mistake. That's not -6. That is +6. Okay, turns out sulfur will have the same +6 charge. So here we've got 4 -2s, which is -8. +6 is -2, so we need another +2 to balance that out. Okay. Water. Hydrogen is not with a metal, so it's going to give away its electron. Water's going to take them to +1s plus -2 gives us that. So what happened here? So let's start with reduced. What was reduced? What lost electron or gained electrons? So lead here went from +4 to +2. That means that it gained electrons. Lead here went from 0 to +2. That's kind of interesting, isn't it? So in order to go to 0 from +2, lead had to be oxidized. Oxygen stayed at -2, sulfur stayed at +6, hydrogen stayed at +1. So kind of an interesting reaction. Lead was not only reduced, lead was oxidized. So out of this, we get our cells. Now the cell here isn't a true galvanic cell. We will not write this into solutions with a salt bridge in between. Actually, they're plates in a battery with sulfuric acid in between to kind of act as a way a conductor running across that. So, but what's interesting about this is lead is reduced, lead is oxidized. What's also interesting about this is it can be easily reversed. And thus you put your battery in your car and you don't have to replace your battery every once in a while or relatively often because it wears out. Your alternator in your car will generate electricity to recharge to cause this to go backwards. So if what'll happen is plus electricity will be a product. Because we're given a product with electricity here, it's going to cause that to reverse. So you can recharge that battery. You only really need the battery to start your car. You have a little motor in there called a starter that starts spinning the engine, and you just need that electricity to get that going, and then your car can recharge that. So this recharging can only happen so many times because there's no such thing as perpetual motion machines. You always don't get the same amount of energy back and forth. That energy is lost to heat, things like that, friction, so it doesn't work. So that kind of covers batteries and redox reactions. Hopefully this was enough information to help you understand it a little better. Again, if you have any questions or concerns, feel free to email me at mrc@mrcscience.com. Thank you.